Yeah, then we will have Carsten van Hansen and Steve Coyne. They will speak about the test method and the metrics.
Okay, good afternoon. It's my pleasure to be here today, and I will follow up Yoshi's talk on the temporal light modulation measurements. So I will briefly discuss the test methods and instruments just to give you an overview, and then I'll come into two of the issues that we have identified into this work. The first one being the power supply selection and its rather drastic influence on the flicker-metric PstLM. And the other thing that I'll touch upon today is actually the calculation of the stroboscopic visibility measure. And that has to do with the frequency analysis and where peak estimation in the frequency domain can give some calculation uncertainties. So I'll show you how we can lower these uncertainties. So for testing of temporal light modulation, TLM, we have some CIE documents giving guidance on this. And then there are the two IEC technical reports for PstLM and SVM that Yoshi also mentioned. Important here is that PstLM requires measurements of at least 60 seconds. And as Yoshi said, we have used 180 seconds for these, for the IC. And the sampling rate has to be 10 kilohertz. For the calculation, when you have a sampled signal, you can do the calculations with the light flicker assessment toolbox, which will do the temporal and statistical analysis. And that is readily available as a toolbox on MathWorks website. For SVM measurements, we require at least 1 second measurement and a sampling rate of at least 20 kilohertz. And for calculations for doing the frequency analysis, there's also a toolbox available. And its uncertainties with this toolbox I'll cover a bit in the last part of my talk today. So this is a schematic of a setup for measuring TLM. You need to have a stable power supply that will provide voltage for the device on the test. Here we have put the lamp inside an integrating sphere. You have to make sure that you only measure the light coming from the light source itself. Then we have a detector looking at the light through a port like this. And then you have an amplifier to amplify the signal from the detector, and you need a low-pass filter before you actually do the analog to digital conversion in order to avoid aliasing effects, which could make large error signals. Okay, so what you get from this is a digitized signal with L samples. The temporal distance here is 1 divided by the sample rate. So the duration of your measurement here is the number of samples divided by the sample rate. Okay. So just a few images from our lab. The lamp on the test is placed within a 1 meter sphere, and the detector here, so this is a custom built system that Yoshi also mentioned some labs are using. We have a detector here, we have a transimpedance amplifier, an anti-aliasing filter, low-pass filter here, and an analog to digital converter. Other labs are using dedicated instruments where all these components are within one instrument. You can also get handheld instruments like this, but it's important to say that when you're doing these measurements for 180 seconds, you cannot use handheld. It has to be mechanically stable. So let's go into this issue about the power supplies. So Yoshi showed you just a brief overview of the different measurement values of the PstLM value. So I've taken for one of the artifacts, we have all the measured values are around the reference value. The reference value is the green one down here. It's a histogram having the PstLM values on the x-axis here, and on the y-axis, the number of labs reporting values in these ranges here. So all the labs, quite a normal distribution as we would expect. But for some of the artifacts, we actually have that. So in this case, the reference value is still down here, very low value, but we have more than 50% of the measured values that are much larger than the reference value, a non-normal distribution. So what is the origin of this variation? As Yoshi just mentioned, when we changed Kiel and our own lab, when we changed our power supplies, we got very much different values of the PstLM metric. So we decided to do some further investigation onto this, doing measurements on PstLM using 3 different power supplies, all set to run at 230 volts, 50 hertz. And we decided to use pure resistive loads. So we used halogen lamps and incandescent lamps. So just show you here. So these are the measurements results. Let's just look at one here. This is the halogen lamp, one of the halogen lamps we have for the power supply number 1, we have a value below 0.02. But as you can see, with the power supply number 2, we have a value that is 4 times higher. And with power supply number 3, we have a value that is 10 times higher, really very much higher. So you could ask yourself, and we see the same exactly the same for the other halogen lamp and similar for the incandescent lamp. Then you could ask yourself, what is actually the reference value here? What should we measure? So in order to say that, we did PstLM calculation for a simulated pure sine wave with the same modulation depth and frequency as we measured for these incandescent lamps here. And then you get the values here. This the light blue values here, you can see they are slightly lower, but comparable to the values measured with the power supply number 1 and far from the other ones here. And then you could ask yourself, but what is the detection limit for these measurements? So we did measurements on a DC stabilized or total flat, should have no temporal variation at all. And then you get values around 0.002. So quite a bit lower than the values that we're actually measuring here. So we can say there's a marked dependence on the used AC power supplies, and we could measure values that are 10 times higher than the expected reference values for these. So we would like to be able to say something about this or indicate the uncertainty that would be using different types of power supplies. So we tried to look into this a bit more, doing the frequency spectra of the measured waveforms. We've done that for the 3 power supplies here, PS1, PS2, and PS3. And what you can see, there's almost no noise. So I'm only looking at the frequency interval from up to 40 hertz. So that's the interesting frequency spectrum for the PstLM value metric. And you can see the power supply number 2 actually has more noise in this region. The y-axis is the same on all these 3. So it's a direct comparison. And power supply number 3 has a lot more noise in this region. So the PstLM value metric is most sensitive at a frequency of 8.8 hertz. So what we did, we looked at the spectral amplitude at 8.8 hertz and tried to plot that versus the measured PstLM value. And that looks like this. So now here on the x-axis, we have the measured PstLM value, and we have the magnitude of this noise contribution for the 3 different power supplies. You see there's a reasonable correlation here. There's a possible correlation to the spectral amplitude. So we're looking at a 1 Hertz window around 8.8 Hertz. We have started a further investigation on this, doing more labs on the same halogen lamps also. Okay. So that was one part of it. The other part is to look at how we actually do the SVM calculations. So that is purely in the frequency domain. The calculation equation is actually like this. Maybe it's a bit too complicated today, but it actually involves looking at frequency peaks in the spectra and comparing or comparing them with the threshold sensitivity of the stroboscopic effect. So that is mainly that. And we can make this a lot easier to look at if we just have a pure sine wave like we had with the incandescent light sources. In this case, the frequency spectrum is only 1 peak, and you can see this dashed red line is the threshold sensitivity function for the stroboscopic effect. So for this sinusoidal waveform, we would expect the SVM value would have a value of 1. And if we, so in this case, we have only 1 peak. So all this summation and quadration up here actually turns out just to be the amplitude of this peak and the threshold function at that frequency where this peak is. So if we enlarge this peak, so we can see the red points are the ones that we obtain from a measurement. The dashed line here is actually the true line behind this, and the peak of this dashed line is the true peak that we're actually trying to measure. So the true value of this SVM is this peak value of the black point and the threshold sensitivity function at that frequency. So SVM calculation uncertainty actually depends on the peak estimation. How well can we find this black point on the curves? Remembering that doing the measurements, we only have information on these red points here. So let's look at a bit closer on this. We only have the red points. So our best estimate for the peak value here would be this one, the highest, the nearest spin peak estimate, you call it. What you can do is to apply zero padding. So you apply a lot more zeros, you double the length of the waveform signal, only adding zeros, but that actually gives us a better frequency resolution, and then we can get a better nearest spin peak estimate after zero padding. And you can apply this multiple times to get closer and closer to the true peak of this. So another way doing FFT contains a lot of calculations. What you also could do is actually to look at the neighboring points of this first estimate. And if you do that, you can actually do a quadratic interpolation, and you can find the maximum point of that, and that will give us an even better peak estimate. And we call that the peak estimate from quadratic interpolation. So let's look at a square wave signal like this. It has many more peaks in the spectrum, as you can see down here. It still has an SVM value of exactly 1. So when we're looking at calculated values over on this graph here, It's actually deviations from the values of 1. The recommended toolbox that is used or referenced in the IEC technical report would give a value. It uses a number of zero paddings. So you can say this x-axis here is the number of times you apply zero padding. So using the toolbox, you will actually get an error of more than 2% for a specific sampling rate. And you can see this point here corresponds to 50 kilohertz sampling, and this point up here corresponds to 20 kilohertz sampling. So we get a large difference, even if it's the same signal, but we're testing it with different sampling rates. And that should not be the case. So if we apply more zero paddings, we can actually reduce the error. But if we use zero padding and the quadratic interpolation, we much faster come. We don't need as many zero paddings, applying zero padding to get to a deviation of less than 0.05%. So you can achieve that with quadratic interpolation and only applying zero padding 2 times. If you don't apply the quadratic interpolation, you need to do it at least 4 times for this specific waveform. Okay, so this was all simulations and calculations. So we also did this by using a waveform generator to generate these signals to show how it looks when you actually do measurements. And we did measurements just like before on the simulation at 20 kilohertz sampling rate and 50 kilohertz sampling rate. And this graph is quite busy. There are 9 different waveforms. Let's concentrate on this one, which was the one I just showed you calculations for. So if you measure that, so I have the 2 different sampling rates, 20 and 50. So the full colored ones are the 50 kilohertz. And you can see using the toolbox with zero padding only 1 time, you'll get more than 2.5% error on this one. And if you use the 20 kilohertz, it's slightly lower. And you can see there's still a large difference here. So what would be the true value here? But if we apply the optimized method using zero padding 3 times and quadratic interpolation, we get a lower uncertainty on this, and we get consistent values for the 2 sampling rates, which we would expect and hope for in a situation like this, right? So I would like to conclude this part of the talk. So the choice of power supply may have a very large influence on the measured PstLM value. And actually the power supplies that we've been talking about, just as Yoshi said, is quite high value power supplies that are used normally in photometric labs. So we need to find a way how to characterize this. And I've shown that the calculation of SVM values from the measured waveforms, it is recommended to use multiple zero paddings and possibly quadratic interpolation to get a good estimate of the SVM value. Okay. So then I'll give the word to Steve.
Okay, for the next part of the talk here, we're going to talk about lifetime testing now. I've got quite a number of slides here, so I'm not going to spend time on each slide with all the details. So I've actually created the detailed slides so you can have those after as part of the pack that's delivered to you. So you've got more information there. Okay, so Why is product lifetime important? This is something we probably need to establish to start with. Why do we need to worry about it? Well, it's a key economic factor in terms of our cost-benefit analysis of the utilising of a product. Along with the lifetime, we need to know about the product price, we know about the product's energy efficiency, known as its efficacy, and we also need electricity price. Those four elements are utilised to determine the return of the benefit that we get from the cost of buying a more efficient product and the less electricity we use. And we typically, as a consumer or a user of these products, we want an assurance that when we're doing these calculations to determine the cost benefit for us, that the values that are provided are reasonable, that we have an assurance of those lifetime values as well as the others. The verification of product endurance lifetimes provides confidence to the market in that they can trust what's presented on the packaging about the product, so they can determine the value to them based upon the price, etc. But unfortunately, with the extended lifetimes that we have for these products now, we can't test till the end of life for these products. As you can appreciate, we're talking about products that have lifetimes 15,000, 25,000, even for luminaires and so on, we're talking about 75,000 hours or more. And if you operate continuously, you get about 8,000, just over 8,000 hours in 1 year. So to test something that's got even a 15,000 hour lifetime, we have to test it for 2 years continuously just to get the results for a product before it can go onto the market. So that's not acceptable. But what we need then is there a way that we can take some measurements of a product under certain operating conditions that will provide us with indications of the likelihood of that product being able to achieve that intended lifetime. And that's going to be important to us. So what is lifetime? There's lots to it. And I won't go through all the details here, but effectively with lifetime, the end of life, there are two basic forms of end of life of a product. One is what we call catastrophic failure. It sounds daunting, but it just means that there's no light coming anymore. And that's typically going to be a mechanical failure or an electronic failure. Mechanical failure is breaking of wires or solder joints, etc. Electrical can be more to do with component failures, capacitors, etc. Parametric failure is, if you like, the gradual reduction in the performance or the functionality of the product. So less light given out, or a change in the color, the color appearance of the product. That's going to be a gradual change, and it'll change to a point where it becomes unacceptable in terms of providing the functions that you're expecting to the level you expect. So that's a parametric failure. And temporal light, as we've just been talking about, that's also going to be a parametric failure as well. The US Department of Energy a number of years ago did a survey of suppliers in the country and looked at and discussed with them about what are the typical failures they're finding with their products, so that we can have a better understanding of how to work with the market. And there's a large number of different failure types that we have in this diagram here, but the ones that are highlighted in the yellow are the ones that were seen as being the most dominant of products presented back to the suppliers, or that were through their own research internally were found by the suppliers, the manufacturers, as the dominant failure points for the products. And as you can see with the highlighting there, that they're predominantly in the mechanical nature and the chemical nature of these products, and also electronic nature. So as I said earlier, mechanical nature and electronic are typically catastrophic failure forms. Chemical tends to be more of a gradual change in the chemical structures, so that's more of a parametric failure. So they're the things that we'd really like to be able to investigate more, is these particular failure mechanisms. So when it comes to then talking about the lifetime of a product, the definition of lifetime of a product is when the 50th percentile or the median product, the 50th sample within a sample set fails. So it's not until all 100% of the samples fail, it's when the 50th percentile of the samples has failed. So the point where we go, we've had 5% failure, 10%, et cetera, et cetera. Once we get to the 50% failure rate within the samples, that's the time that we classify as being the median lifetime of a product. So with a classic cumulative failure probability curve, that's this blue line here, where this is operating time on the base, and up here we've just got the failure probability, cumulative failure probability. So at the top here, 1 is 100% all samples have failed at that point. So the blue is the typical curve that we would see. And at the 50% failure rate here, we're looking at, with this particular example I've got, around about a 15,000 hour is the median life of this example that we would have here. So that's okay. What we don't want to see with a product in particular is where there is some early failures with the product. If we have a significant number of early failures with the product, that is what's going to be most noted by particularly consumers when we talk about consumer-based products. So you go buy a product, and within the first month, 2 months, that product fails. You remember that you only bought that a month ago. So that is most off-putting for you as a consumer, and it also is rather unfortunate in terms of the telling nature of the product, in that after a fairly short time, potentially there could be up to 30% of the product has failed, but in terms of its median lifetime, it still reaches, the median lifetime is 15,000 hours. But we've had a lot of early failures. So in this example here, nearly a third of the product has failed after about a third of its lifetime. That's not acceptable. So is there ways that we can test for that early failure rates? So if we look at the standards, we have the IEC standards. The 62612 is the performance standard for LED lamps. And then we have 62717, which is the performance standard for LED modules. Within both of those, we have endurance tests written in there. There are 3 of those. One is what's known as accelerated operational life. So it's put at an elevated temperature and it's operated continuously for 1,000 hours. If it's operating at the end of that, it passes the test. The second one is an ambient temperature cycling. So it goes from -10 degrees Celsius to around about 40 degrees C. So that's typically the operating range that the supplier will give you for their products. So we cycle through that temperature range. At the same time, we also cycle the product off and on in an asynchronous cycle. So 34 minutes on and off, as opposed to a 3-hour cycle through the temperature ranges there. And we do 250 cycles. At the end of that, if it's operating, then it passes. The final one is a switching test, where we effectively is just switched on and off at 30-second intervals. And the number of cycles is half of the number of hours of lifetime of the product. So for instance, if we have a product that is has a 15,000 hour lifetime, then half of 15,000 is 7,500. So therefore we switch it on and off 7,500 times. And in that example, that's about 125 hours to do that. If it's operating at the end of it, it passes. There's currently a review of these standards, and that review is actually consolidating both these standards into one standard, which would then be known as the LED light sources performance standard. And that includes all of these existing endurance tests, but it also includes some informative annexes that's going to include lumen maintenance test methods, which are not currently within the standards. One of those annexes will be the European current endurance test, which I'll talk more about shortly. And then also the more accepted one that's been around internationally for a number of years is the IES of North America, has an LM80 test method. The LM80 test method is, if you like, the gold standard, but it is still a significant test time. We need up to 6,000 hours of testing as a minimum. And with that, there is no switching, but we take a measurement after every 1,000 hours and we plot that. So we end up with our 7 measurements from the initial and then each 1,000 hours after that. And then that gives us enough information that we can then extrapolate from that to get where it would extrapolate down to a 70% lumen output of the product from its initial output, and that will be deemed to be the lifetime of the product. There is a limit to how far you can extrapolate out from a statistical point of view. We haven't got time to go into it, but effectively you can go no more than 6 times the number of hours of measurement. So if you only test for 6,000 hours, the maximum you can extend out to is 36,000 hours. So this one here goes beyond it. So all the statement technically could be is that the product lifetime is greater than 36 hours. You can't actually stipulate that it's in this situation here around about 45,000 hours. These are the standards that are used for the testing and also for the prediction, the analytical methods. The IEC has utilised some of that information in their standards, and I definitely won't go through all of this here, but it's all there for your benefits. That if we look at an LED product, I've just said a lamp here, but it can be any LED product. If it's constructed from the use of some LED components, for instance, it contains an LED module within that product. The OEM, what's known as the OEM or original equipment manufacturer, who supplies the modules that then goes to the final product assembler. If they have tested their modules because they're trying to market those to the assemblers, they will have test data on the performance of the module at different temperatures and different currents. If you have that information, then you can, the test reports are available for that. Then there is a reduced amount of testing needs to be done on the final assembled product. In fact, it could only be an hour's worth of testing that's required. If you don't have that, the product has an LED module in it, but it has not been tested as just the separate component, then it's 6,000 hours of testing that's required. For an LED lamp that contains an LED package, similar sort of scenarios here, where we've got, again, testing arrangements, whether you've got test reports for that LED package or not. And then at the end here, we've then got the European current endurance testing, which can be used on all products, no test report required for any components. And we do testing for 3,000 hours of operation. And then we've got a prediction here. The difference being that these here are predicting a lifetime, as I showed you, a projection to a point. The EU form here is that the formula is to determine the minimum lumen maintenance of a product based upon the claimed lifetime on the package. So in other words, we test it for 3,000 hours and we get the lumen maintenance of the product. But then we look at on the claimed lifetime, and then on the claimed lifetime, we do a calculation and say, well, for that claimed lifetime, after 3,000 hours of lifetime of operation, what should its lumen maintenance be? And if those two correlate and they relate to each other, then it passes. So it's not doing a full lifetime test, but it's checking on the, if you like, the validity or the confidence on the packaged information. The European test method then is 2.5 hours on, half an hour off, 1,200 cycles for the 3,000 hours. And 2 criteria. One is that only 1 sample out of 10 samples is allowed to catastrophically fail out of that testing. And then, as I said, we've got to have this check here of the lumen maintenance of the actual, after 3,000 hours, has got to be greater than what is the minimum that is claimed when you use the L70, the lifetime claim from the manufacturer. So how does this all come about, or how does this work? Well, we, part of the Australian contribution towards the SSL Annex back in 2018-19, we actually did this investigation to start with. So looking at the testing the time on and off, and using close to what was the IEC. The IEC, as I showed you before, for switching was 30 seconds on and off. Here I did with 1 minute on and off, just because of the equipment we had at the time. Looked at 3 different products, 2 lamps, one that was very lightweight, 65 grams, one that was quite heavyweight with a fair bit of thermal mass in it, and then also a downlight that had a remote driver. And here we can see the cycling for each of these products. So 2.5 hours on, then half an hour off for this particular product, then 2.5 hours on, half an hour off. And for this particular lamp, we see that the variation in the temperature is 45 degrees between the maximum and minimum, Whereas over here, when it's turned off and on at 1 minute intervals, it's only a 12-minute variation, 12-degree variation between the maximum and minimum. Slightly different here for this product, but still significant, 44 degrees difference between max and min with the long cycles. Here we've got 4 degrees minimum between in maximum and minimum with 1 minute cycling, and sitting at around about 45 degrees. So this is almost like Goldilocks and the Three Bears. This is just right in terms of the nice comfort zone for electronic product. Very little variation in temperature between max and min, and sitting at a fairly reasonable ambient temperature of 40 odd degrees, as opposed to being up at the 60 to 70 degrees and dropping down to very low levels. This sort of variation in temperature creates a lot of expansion and contraction of the components within the product. So it really does stress mechanically the product, and that's really what we're trying to look at in this situation. So to further that investigation, what we did in Australia, we looked at 20 models that were on the market at the time, took 5 samples of each, sent them off to an accredited laboratory where they operated those 30 seconds on and off for the required number of cycles. Out of those 100 lamps, 0 failed. They all still operated. Out of those 20 models, we then took 11 of those products, 11 models, and took 5 samples of them, and we conducted that 2.5 hours on, half an hour off test. And for those products, we found that there was 2 of those models, virtually 100% failure of the products, catastrophic failure. 5 out of 5 samples failed, total failure, catastrophic failure. And for this particular product here, 3 out of 4 failed. When we looked at the lumen maintenance on another 2 of the products, we found that the lumen maintenance level of around about 89% here was actually below what was being claimed in terms of the lifetime that was claimed by the manufacturer. The lumen maintenance should have been no less than 93%. So again, we have failures here. And we have other ones here that look like they should be failing, but there was no actual claim on the package at the time. It was not a regulated product, so it wasn't mandated to have the lifetime claim, but they look suspicious. This one here is below the 70% anyway. So after 3,000 hours of operation, it had already failed parametrically on being less than 70%. So you can see that the test methods seem to work. With some of the catastrophic failures, some of the products were then broken down to investigate why they failed. And here's just a couple of examples. There's explanations of them, but the wire connection between the electronics and the base of the lamp had disconnected from the cap. And then we have here, it's a bit hard to see, unfortunately, but we have a delamination of the phosphor on the LED filament in this particular one here. So can we reduce the time that we use for testing? That's really what it comes down to from government regulations and burdens on the industry as well as on compliance programs. And that's what the annex is still continuing and endeavouring to do. It's really one of the things that it's probably most important to us in moving forward. So there's one investigation we've been doing over a couple of years now. Just go through this very quickly. There's some formulas here I'm not going to spend too much time on, but at least give you an indication what we're doing. This is first part of this investigation is doing an accelerated depreciation test, where effectively we're operating at an elevated temperature, these products at 60 degrees C, and we're doing it for 1,500 hours. And from that, we can actually get a lumen depreciation, but it's at this high operating temperature. But it will accelerate the depreciation of the product. So that will give us some good information, and we will get information on that rate of depreciation of these products. The theory is that if we can use that information associated with that accelerated testing, so accelerate ADT is the accelerated depreciation test, we have some particular values within formulas that can be included to assist us, but we also need some other parameters included, the values of them, from what is known as from some pulse soak tests. Now, what are pulse soak tests? Pulse soak tests where we will measure a product at startup. So immediately at startup, we measure the lumen output. And then once it has stabilized, completely stabilized its lumen output, we measure the output again. And we will do that with different ambient temperatures from 25 degrees C to 40 degrees, all the way up to 100 degrees ambient temperature in 10-degree steps. Now, what's this pulse soak test look like? Here's an example of the measurement. So the purple line here is the voltage being switched on. The voltage is on the right-hand side here. So at 0 seconds here, the power is turned on, power switches on, and then operates at the 230 volts. Here is the light output, takes around about 150 milliseconds for the light to actually turn on. When it does turn on, it actually gets up to quite a high level here. This is all relative to the final stabilized value of, is at 1 here, relative light output. So here it's got up to nearly 50% higher than its stabilized level, so nearly 1.5. You can see that it drops down, it starts to drop down very quickly. So within 200 milliseconds, we're starting to get a drop in the light output. So obviously the chip is heating up. And at that point there, the heat is having an impact on its light output and it reduces. And then over the next 15 to 30 minutes, it then drops down to this point here, which is our relative value. So this here is our what's known as our pulse measurement value, the luminous flux output here. And then the soak is then the value that we would measure at that stabilized level later on. And it's quite different for different products. So that 1.5 level for the pulse there, for some products it might only be 1.1, 1.15, etc. It can vary. So that's why we do the testing. In terms then of continuing doing the testing, as I said, at different ambient temperatures. So for the pulse test, we would then stabilize the product at, for instance, 40 degrees ambient. And then we would, once it's been stabilized, so we know that all the componentry within the lamp is nicely stable at 40 degrees ambient, we'll then turn the lamp on, immediately measure the luminous flux, and then we will wait for it to stabilize and we'll measure the level again. So at temperature 1 here, the ambient, when we turn it on, it would be this luminous flux output here, at the top here. And then after it stabilizes, it has dropped down to this point here. So that's soak point, okay? And as you can see with product, as we use a higher ambient temperature, this is the initial turn on luminous flux, but most of the times there'll be a greater drop down to the stabilized luminous flux output down here, okay? Well, how does that help us? How that helps us is when we have a product, we turn it on and it's at this ambient temperature here, we said that the soak test will get to this point here. It will drop, we'll start here at the pulse, but we'll drop down to the luminous flux output here at this point. That luminous flux is the same as what we got when we did the pulse test. So the initial output of this particular point here, when the chip, when it's just turned on, but it was at this ambient temperature here. So in actual fact, when we have an ambient temperature down here, we turn on the product, it started at this temperature, the light output was equivalent to this, this temperature here. So the chip is operating when it's stabilized here, right, at this ambient temperature. This effectively is the junction temperature of the chip inside the lamp. With that information, then we can then put it into all the formulas and we're able to then determine those coefficients we needed for in the formula to determine a potential lifetime. So we took we've then taken 5 different products of various types, won't go into the detail there, but different lifetimes, different powers associated with them, different color temperatures, so different amount of phosphor inside. So here you can see some of the test results. On the left-hand side is where we do the accelerated aging test. So it's at 60 degrees constantly, and every 150 hours, we take it out of the chamber and measure the light output. And this is the 5 samples that were operated within the chamber for this particular model. This here is, if you like, our reference point where we had 5 samples that just sat in the chamber but were never turned on. But we tested them anyway, and you can see there was no impact on lamps being stored at 60 degrees in terms of their performance when we took them out to turn them on. Over here, we have the pulse and the soak tests. Again, we have the measurements here for these particular products, with the pulse test being at the top, and then we've got the soak test being the dashed lines. Down below is just the mean for each of the 5 samples that we're looking here. As I step through the next few slides, you'll see how there is a difference here between this particular product. The next one, less depreciation on these products, and less of a slope on the right-hand side with the pulse and the soak. Okay. When we take all of that data from all of that testing, get those coefficients for those formulas I showed you earlier, we end up with a prediction on what the lifetime should be for these products when they're operated at the normal ambient temperature of 25 degrees Celsius. And you can see here for that first product, it was 1,700 hours is the lifetime of it, yet it's rated by the supplier for 12,000 hours. We got nearly 5,000 here, rated for 15. But then at the other end, you can see we've got some product that is performing or predicted to be 23 to 43, but only claiming 15,000 hours. So some products are good, some products are concerning, as we've seen here. So as I said, this is just research at this point in time trying to verify this process. So what we need to really do is compare that to the gold standard for lifetime testing, which is using that 6,000 hours of testing. So at the moment, we have another 5 samples of each of these models is now being tested for the 6,000 hour testing by the Swedish government through their national laboratory, and they're conducting the testing. At the moment, we've got test results for up to 2,000 hours. Next week, unfortunately, not this week, is the 3,000 hour test result. So we'll have that end of next week. It's just timing, it's life. So we'll have that, but then we've got another 4 months to wait until we get to the end, to the full 6,000 hours test. And hopefully what we'll find is that the lumen depreciation that through the gold standard test method that takes 9 months to test, hopefully we'll verify the results we have from this predictive model here, that only takes a maximum of 1,500 hours of test time requirements. Okay, so in conclusion then, the annex is going to continue this work as we go through. The annex, the last couple of years ago, we actually commissioned researchers to do a literature review on all of the lifetime publications and material that was out there. There's a link that will be as part of this, slide set that will go out to you, or even to the SSL Annex website. You can find that particular report there. Ultimately, may resolve this test method. We may need to separate methodologies for affordable short life domestic type products, so like that 10,000 to 15,000 hour product. This might be a good test method for that. But then when it comes to commercial products where we've got, if you like, outdoor lighting, street lighting, so on, where we're talking about products with 75,000 hours or beyond lifetime, we may need a different test method for being able to try and to verify that. So the desirable information to have is on early failures and that median lifetime. Really, that's the critical thing that's important, particularly to consumers. Right, so ideally we want a test methodology that is non-invasive, it's short duration relative to the product life, limited sample sets required, so not over the huge amount of testing, and easily obtainable measurement, what we call measurans or test results. And it covers the assessment of dominant failure mechanisms that we spoke about earlier. Okay, thank you.
Thank you, Stephen. Thank you, Carsten. Well, we have time for a couple of questions. No questions from the room. We have something, yeah.
I have a couple of questions here. This is Mike from the SSLC platform. We have 3 questions in the Q&A for the folks online, so maybe we can start with those. And I think this first question is for Carsten. Carsten, has the recommendation of is it quadrilateral interpolation, QI? Has the recommendation of QI been shared with CIE TC 2.89?
So I'm not sure that.
No, but it will be.
Into the microphone, please.
Sorry?
Into the mic.
Yeah, so So I'm not sure that it has been formally shared. It has been published back in 2022. And as one of my colleagues is actually a member of the TC 289, I'll make sure that it's formally shared in that respect also.
Okay, great. And then the next question here, I think it's, well, could be for either of you. Is it planned to also include possible measurement uncertainty calculations for the TLA values in future standards?
I think that's the hope, is that for all test methods, the values are of little value without having an uncertainty assigned to them. So yes, I think that would be the hope and the expectation, is that we can be at a point where we have uncertainties for our measurements.
Okay. Do you want to add anything, Carsten?
Yeah, I think it's very important, and especially when we see issues like the power supply issues here, we have to be able to attribute uncertainties on the different parts of the measurement schemes, and the power supply. We need to be able to set uncertainty from that part of the measurement also.
Great. Now, the next comment I think is more in Steve's direction, and it's a comment from Lawrence Sparling. Lawrence just says, FYI, in the latest draft of IEC 63555, which is TC 34A 2395/CDV, the endurance testing has been removed.
Okay, thanks,
Okay.
Lawrence.
Okay, thank you, Lawrence. And now a question again for Steve, and this is the last of the ones, and just checking here, why would the shortened lifetime prediction method only be applicable to consumer products?
The concern is just about the amount of lumen depreciation that would be there for long lifetime products. And I think that's sort of seen in the European regulation with the formula that's used there. You know, there's a limit of utilising the formula in the test method to lumen maintenance maximum of 96%. And so you're getting to the point where we need to have a better understanding of the uncertainties of measurement and the repeatability of measurement of laboratories to be able to improve that and the uncertainties of measurement, so we can get a more precise determination of what that lumen maintenance is for those projections.
So the folks who asked those questions, if you have follow-ons, please feel free to put your hands up and I can unmute you. Otherwise, that's it for the Q&A online, George. If you want to check the
Okay,
room.
thanks. Any additional question from the room? I have one for Steve. When you saw the light coming up, you know, the pulse effect, why this pulse effect exists? What is the reason?
It's the change in temperature of the chip from when the current first goes through. The chip is effectively at ambient temperature, and as soon as the current is passing through it, with the resistance to the flow, to the current flow through it, you're increasing the heat within it, and it immediately starts to increase in temperature, dropping the luminous flux.
Okay, and that means it's not an artifact.
It's not an
from
artifact.
it's a physical. Okay.
What initially intrigued me was the speed in which the luminous flux dropped. After 200 milliseconds, you had that immediate drop off, and that was consistent along with all of those products. That was because when we first started doing the testing, I suggested to the laboratory that I wanted them to capture that pulse within the first half second, so 500 milliseconds, which is what they did. They set their data recording to 500 milliseconds. And then when I looked at the results, something was wrong. I couldn't understand. Then I went and looked back at the full data, the data file, and saw that we were actually missing the peak of the pulse peak by taking the recording from out of the measurements at 500 milliseconds. So then we had to go back to the laboratory and say, change that, let's get it within that 200 milliseconds.
And you see it to all products?
from the ones that we were doing,
Yeah.
yeah, it was fairly consistent to be within that.
I'm very curious to see if we can simulate
Yeah, yeah.
this effect. Most probably yes, and we may maybe get some very interesting information about the dissipation, thermal dissipation behind the chip. Yeah, okay.
Yeah.
I will think about. Thank you. Okay, if no additional question, I think it's time for coffee.